So good morning. Let's start our session today. First reporter, S.Shmatov, Dubna, CMS overview. Sergey, do you hear?
Yes, can you hear me?
Please.
Okay, the slide okay? Okay, I'll start. Good morning, dear colleagues. Today I would like to, with great pleasure, to present a brief review of the CMS, of results of the CMS collaboration. As you well know, the CMS is one of two largest experiments as a Large Hadron Collider. It brings together over 6,000 participants from 57 countries. Among them, there are 3,400 scientists, over 1,100 engineers, and almost 300 technicians. My report includes highlights from physics results for the standard model, Higgs physics, search for new physics. Today, the collaboration has published 1,210 papers on collision data. Here are the distribution of this article over time and physics direction. Indeed, I do not have time to touch of even a small fraction of all these results. So everything that I will show is my personal choice. But besides, I would like to draw your attention to the fact that the more nice talk with SMS results will be presented at the conference. So I address you to these reports for details. Also, you can use some links as a reference for a detailed study of our results. Round 3 has started in July 2024 with 13.6 TeV, and now we have about 64 inverse femtobarn of recorded luminosity. The expected value is about 260 inverse femtobarn by the end of the round 3. And today, the number of PP interaction per beam crossing, so-called pile-up, is reached 52. Also, the CMS collected and analyzed heavy ion collision. Review of these results will be presented by Sergey Petrushenko. But before moving to the physics results, I would like to say a couple of words about the preparatory phase and show the most recent example of studying the detector performance. The first and second LHC long stops were focused on the phase 1 upgrade of the CMS detector to ensure the effective operation at high luminosity of more than 10^34 as the nominal LHC energy. During LS2 work on barrel hadron colorimeter were completed. Critical parts of the muon system upgraded has been finished, and beam pipe and pixel detector installation were completed before startup of round 3. During detector commissioning as the last year, we gained an understanding of the impact of detector performance at high instantaneous luminosity. For example, it has been shown the linear continuation for the strip tracker and high heat efficiency for the picture, for the pixels. I would like to start the discussion of physics results with the standard model, and namely with the slide where presenting the summary of standard model test based of measurements of the total cross-section for the different processes, namely the QCD, single boson production, diboson, triple boson, and the process with vector boson and vector boson scattering. From the very beginning, LHC capabilities provide enough statistics to study inclusive and differential distribution and make precision measurements. Deviation from the standard model expectation may indicate presence of new physics and can be used for the effective field theory interpretation. And this summary plots for different electrolytic processes demonstrate precision measurements that are in good agreement with the standard model as a scale from the millibar up to femtobar. And the first flash result of round 3 is the first measurement of the Z-boson production at 13.6 TeV. It was done in decay channel with a pair of the muon in the final state that allowed to measure product product cross-section and branching fraction with a good accuracy. The measurement is done in the fiducial region defined by the kinematical acceptance of the CMS detector and extrapolated to the full phase space, resulted in the total cross-section for the boson production. The fiducial as well extrapolated total results are both dominated systematic uncertainties in agreement with the results of the previous run 1 and run 2, and theoretical prediction calculated as the next to next leading order accuracy and the recent Parton distribution function. Measurement of multiple boson produced simultaneously are key to testing the electroweak scale sector of the standard model. The non-abelian nature of the electroweak interaction predicts the presence of self-interaction vector boson. Many multi-boson processes are only accessible as the LHC due to its high collision energy and large amount of data. Recently, CMS reports the first observation of WW gamma production processes. The measurement fiducial cross-section in a good agreement with the next to leading QCD prediction and the value of the question given here. In the standard model, the contribution of the longitudinal polarization component of vector boson scattering is very small and very sensitive to processes beyond the standard model, the very effective beyond standard model. CMS investigated for the first time the electroweak production of the same sign W boson pair with which hadronically decay into the hadronically decay tau lepton in the final states. The observed signal significance is 2.7 standard deviation. The stringent test of the standard model also have been performed using the channel with the particle produced in association with jets. Here I put the summary of the cross-section for gauge boson of pair or pair of gauge boson, pair of T quark, Higgs boson. All measurements agrees with the standard model prediction. Physics with jets also provide tests of the quantum from dynamics, both in the perturbative and non-perturbative regime, and as well as it allows us to look inside proton to constrain PDF and to measure of QCD running coupling. The current measurement of the jet PT spectrum demonstrates agreement with next leading order in general better than for leading order. The associative production CAB quark with gauge boson are used to probe the strange and boson quark contents of the proton. And again, I refer for detail for talk by Olga Kozlova. Starting from the run 1, the LHC is considered as top factory. Above 200 million quark pairs were produced during LHC Run 2, 813 TV. And this spring, we present the first measurement of top quark pair production, 813.6 TV. Here presented the energy dependence of pair top quark production. Data was recorded in summer of 2029, and the statistic corresponds to integrated luminosity of 1.2 inverse Ventabarn. All event were selected with 1 or 2 charged leptons, electron muons, and we require the additional jets in final state. All inclusive TT production cross-section in agreement with the standard model. Also, I would single out to see 2 new results on top physics. This observation of 4 top quark production and first evidence of TWZ production. Both of them are among the rarest standard model processes currently accessible as Hadron Collider. They have unique features that make it suitable to probe several interaction in the standard model. For example, for the first one, for top quark production provide a way to measure top quark Yukawa coupling complementary to its extraction from measurement of Higgs boson production in association with top quark. And of course, CMS produced many new results on rate decay of big hadron, meson, etc. To perform in particle to test lepton flavor universality. In the conference agenda, we have 4 nice talks on this subject, so I refer you to this report. Since discovery of Higgs boson by Atlas in CMS collaboration in 2012, an extensive program has been performed to study its properties and testing its compatibility with the standard model. By now, the Higgs boson has been observed in all many main decay modes, and many production channel has been studied. One of the most important results of Run 2 is the first evidence of coupling of the Higgs boson with fermion of the second generator. Here you can see the nice picture with the Higgs to muon candidates in gluon fusion channel, and the total excess of event over the background expectation was observed with significance 3 sigma. The measured signal strength, not contradiction with the standard model, the signal strength relative to standard model prediction is 1.90. In the next step, we tried to search for a number rare Higgs decay, and as a result, CMS and Atlas collaboration obtained the first evidence of Higgs to Z gamma decay with significance 3.4 sigma. Another decay, Higgs into fermions of the second generator, namely C quark, is not visible so far, but we set the most stringent limit on the value of couplings. Differential Higgs boson production cross-section are very sensitive probe for physics beyond the standard model. New physics may contribute in gluon-gluon fusion loop and manifest itself through deviation from distribution. A new set of measurements designed to quantify the different Higgs boson production processes has been performed in gold discovery decay, Higgs decay into 4 lepton and 2 gammas. The different cross section are determined as function of the transverse momentum and rapidity. Higgs boson number of associated jets and transverse momentum of leading jets. The limit, we obtained the limit for the coupling Chi-B and Chi-C. And finally, speaking about the Higgs physics, the Higgs self-coupling can be studied in Higgs pair production. Here we don't see clear signal of such processes. CMS just set limit on the cross-section as the level of 3.4 of the standard model prediction. Right from the beginning of time, CMS also developed a broad program searches for physics beyond the standard model. From the experimental side, now it's based on the direct searches, including so-called conventional signal like new resonances and dilepton, dijets, diphotons, or non-resonance signal in this spectrum combination of physics objects with missing T, B, and T, tagging high multiplicity events. It allows us to search for the SUSY, extra dimensional extended gauge boson, and many other predictions from scenario of beyond standard model. And later we active use on conventional signal, for example, displaced vertices, leptons, jets, dileptons from long-lived particles, or emerging jets and leptons from boosted heavy object, I mean high PT, Z, W, Higgs, etc. The specific trick of the last year is to use the Higgs boson as a tool for new discovery. Also, new physics can be properly checked for discrepancies with data and search for new physics via effective field theory and precision test of the standard model. This slide summarizes the results of direct searches for new physics with conventional signal. Here are mass or energy scale limit for contact interaction, RPV, SUSY, KK graviton, which come from extra dimensions, excited fermi and heavy gauge bosons. Further, I'll just show a number example of these searches. And the first of them is a pair of particles of electron muon gammas gauge bosons as a standard candle to search for new physics. Many scenarios beyond the standard model predict a new heavy resonances which can be proper in such channel. And historically, we try to find excited graviton, boson, U-gauge boson, contact declaration, test, lepton flavor universality. Unfortunately, no significant deviation is observed with respect to the standard model background. And for a moment, we can measure upper limit on cross-section of this process and set new stringent today lower limit on the model parameters. Also, this channel can be extended to use them as a purpose. The dark matter candidate that, okay, I see. That interact with the standard particles through a spin-1 mediator, which can be vector or axial vector. Again, we just set a new limit on model parameter. It can convert our result and upper limits. The most complicated scenario will be reviewed by Marie Savina. Beyond standard model searches, weak Higgs include looking invisible exotic decay, additional extra Higgs, lepton flow violation decay, and the couple examples. The first of them for the looking for invisible Higgs, the expectancy rebranching fraction to the invisible to nothing is very small. The several BSM scenario predict anomalous insizable value where the branching is significantly enhanced, and vector boson mechanism of Higgs production allow us to search for this decay. The observed upper limit on the visual branching fraction was found to be 0.18. The properties and decay of the Higgs boson are thus far consistent with expectation of the standard model. However, there is a considerable motivation to search for BSM decay, and the lepton flow violation, the Higgs can provide the possible signature for such processes. These decay are forbidden for the standard model, of course, but arise in model with more than one Higgs doublet or certain symmetric model, etc. CMS report a search for lepton flow violation decay in mu tau E tau channel. No significant excess has been found, and results can be we have interpretation that results in terms of upper limit of lepton flow variation branching fraction. The value is given in this slide. In case mass of Higgs is larger than double masses hypothetical particles, some BSM scenario allow Higgs boson decay into the two hypothetical on-shell pseudoscalar a scalar particle decaying on the pair of standard model. For example, the X-ion particle or dark photon, the limitation is given here. And from the other hand, is a hypothetical particle have masses larger than Higgs. They can decay mode can contain Higgs boson itself. For these searches, we have some experimental requirement in model dependent limit on the production cross-section of the spin 0, spin 1, spin 2 heavy resonances are derived as function of mass of these hypothetical particles. These reported bounds are the most stringent to the day. And the LHC also could produce many long-lived particles with masses from MeV up to TeV that would lead to signature involved displaced vertices of standard metal particles. CMS already produced with run to date above 35 analysis on search LLP, and their interpretation within SUSY scenario with violated and conserved R particles, as well as with extended Higgs model. And just two examples, the dark sector particle continued traveling for a long time and transferred several meters before turning back quantum mechanically in the visible universe. In this case, the Higgs boson is likely to be one of the candidates for the messenger between our universe and hidden sector. The particle shower from LLP decay would reconstruct as locally highly multiplicity cluster in the gas detector signal. This experimental signature is very similar to jet. Like in jet calorimeter, the LP produced a showering in the muon system. One of the most sensitive variable is the search the number of the hits in the cluster. You can see in this distribution. And strong constraints are placed on proper decay lengths of the particle to be between 1 and 100 meters. And another example is the inclusive search for exotic massive LLP decay into the pair of the opposite charge muons referred as displaced muons. This signal originated from common secondary vertices, special separated from interaction point. We have interpretations results of the search in the framework of two benchmark models, hidden abelian model with dark photon, and simplified model, which non-standard Higgs decay in this some type of the long-lived particles with the muon and fermions jets in the final states. And finally, I would like to say a couple of words about our plan on the LHC upgrade. The JINR LS2 to the major LHC upgrade to high luminosity is planned to ensure feasibility of the high luminosity program. The SMS detector have to be upgraded to be able to run the significantly rising level of radiation. The mean pile-up will increase by about factor 3 up to 140 with impose additional requirement on performance of the detector. Now we reach excellent progress in all projects, all technical design reports. More physics projects for high luminosity starting to be appear that beyond my talk. In my summary, I would like to stress that CMS physics analysis of run 2 and phase 2 upgrade activity are going well enough. Many new analyses became public for summer conference and available as public briefing. Run 3 is going well enough and many new unconventional signals are used for searches, and we are looking forward, I hope, for the new physics. Thank you for attention.
Sergey, for the very nice survey. Please, questions. Maybe some questions from outside. Yeah, please.
I have a question about very low masses. What is, do you plan to study couplings of more couplings of the Higgs to electron, electron plus Z? What is the status of that? What do you think will be the progress on this? Do you consider this interesting or not so much, maybe?
Yeah. I believe that very interesting question and a very interesting signal, but the probability of these processes, I'm afraid, doesn't allow us to study these processes right now with the currently collected data, but probably in the future we can do it. I don't know exactly and I don't remember the number of this probability, but if we're looking for another rare decay, say the Higgs into the 2 electron, that I can say that is this study of this decay beyond of the LHC possibility, even for the high luminosity regime. Unfortunately, maybe if we have the physics beyond the standard model, it can be, this channel can be enhanced and we be likely to see it, but I'm afraid that within the standard model, it will be a very difficult task.
Thank you.
Any more? Sergey, very short question. Could you comment? You mentioned non-standard Higgs physics in your talk.
Yeah.
So every week we can see in Inspire one paper about gamma signal at 95, and sometimes mu plus mu minus signal at 28. What is the real significance of these two guys? Could you give a brief comment on that issue?
I'm sorry, you mean you mean the probably access in the region of 28 GV, yes or not?
Yeah.
Okay, yeah, I have the additional slide, the current situation that we see this access in the run one data, but unfortunately the kinematical requirements and kinematical restriction for the run 2 does not allow us to see it right now. The kinematical requirements should be optimized for run 2 data. After that, we can conclude something more in details. I cannot say something more because this information, no, in general, this information only private for collaboration.
Okay, thank you very much. Let's thank you very much, Sergey. Once again, let's thank the speaker. Let me give the floor to the next speaker from INR, Alexander A.Furs, luminosity determination by Alice during LHC Run 3.
Actually, I'm A.Furs. Okay, thank you. So in this topic, I would like to present a quick overview on the luminosity determination by Alice during LHC Run 3 data taking sessions period. And also there will be information concerning previous results in Run 2 and a quick status report of the current situation at Alice. Okay, so let's start. As you know, luminosity is fundamental parameter in collider physics, so it can be expressed as two items: instantaneous luminosity, which represents number of collisions per second, and integrated luminosity, which represents number of collisions per given data sample. So you know that cross-section is luminosity is involved into the cross-section calculations as the ratio between number of the process events and divided by luminosity. Uncertainty of luminosity is also an important factor which helps us to determine determination of the source of different systematic errors. It helps to understand and a fraction of influence on cross-section calculation, and of course it helps to understand for the next modifications in experiment setup and for the analysis. Also, luminosity measurement important for the online mode. For instance, for machine optimization, rate leveling of the beam and beam quality monitoring. Also for luminosity accounting. So at Alice, luminosity determination is based on the detector luminometer visible cross-section calculation, which is actually a fraction of the inelastic events, fraction of the cross-sections of inelastic process, which satisfies trigger conditions during the detection. Then luminosity can be indirectly expressed as the ratio of the visible cross-section rate of the visible cross-section rate of the luminometer divided by its visible cross-section. So initial luminosity of an accelerator formula is given this. Was there? So as you can see, this slide, this formula is the initial formula for Thank you. So this formula includes accelerator frequency, bunch intensities, and beam overlap integral with normalized particle density per bunch. In case if we consider that during the session we have a beam separation, then final visible cross-section can be expressed as the integral of the function of the luminometer rate as a function of the beam separation, or let's say beam displacement. So here in this formula, you can see a trigger rate function of a given luminometer and beam shifts along given plane, let's say XY plane, which is perpendicular to the beam direction. So finally, if the factorization stands, which means that a rate function can be expressed by two independent components, which is rate along a given axis, then the whole formula can be expressed as the head-on rate and also multiplication of two effective beam width, which is integral of the each rate function along given axis, integrated by displacement and normalized by head-on rate. Then the final luminosity can be expressed via head-on rate and visible cross-section. So the main purpose, the main task is to calculate these two effective beam width. For such calculation, one need to provide special session named Vandermeer scan. It contains main stage, which is during that stage, one of the beam is fixed at the head-on position, while the second beam is shifted along the given axis, X or Y, in both directions. So in total, there will be 4 steps, 2 axes, 2 directions. So during that session, we collect data for observing rate function. Then, of course, it will be fitted, and the final calculations of the effective beam width will be done by using integral under this function with normalization by head-on rate. So as you can see, this illustration, the edges two beams just slightly overlaps each other, partially overlaps, and fully at head-on position fully overlaps. The second part of this session is, of course, because of imperfection of the experimental step, one need to apply special corrections. So some correction needs special substages during that Vandermeer session. Here presented a list of the items for a given variables which is required for this. First, it's of course step correction. For this such step correction, one need to do special second substage, which is long scale calibration during Vandermeer scan, and also additional orbit drift correction, beam deflections. And one important remark during this presentation, details is provided only in the backup slides, so we will not focus on each of these correction. Second item is the bunch intensities due to the some components such as satellites, ghosts, which will be explained in the next slides. Such components should be also removed from the bunch intensities. Of course, luminometer suffers by background, pile-up, beam decay. For instance, nominally, Vandermeer scan takes up to 2, 3, or maybe 4 hours. This means that beam decay also should be taken into the account. And non-factorization effects. So for this component, we study luminosity, or we study luminous region by using vertex data, and we use special third stage offset calibrations, first stage of the Vandermeer scanning. A few words about Wide Chasm Collider. So firstly, one accelerator orbit contains 3,564 bunch slots, each 25 nanoseconds length. One bunch slot contains 10 RF buckets per 2.5 nanoseconds each. So nominal bunch, if charge, nominal charges are focused on the our bucket number 6. So also we have 4 beam masks for each bunch. Empty means that nominally there are no charge in a given bunch slot. Beam A, beam C means that in a given beam A or beam C, there are nominal charge. And both beam means that both beam A, beam C in a given bunch crossing ID we have. Oh, sorry. So in case of charges out of the nominal RF bucket within nominal bunch slot, then it means that there are satellites. And charges in bunch slot which are not nominal, which means empty BC mask, means that this bunch claimed is the ghost. So these two components should be excluded from the bunch density calculation. A few words about ELIS experiment. So main goal is to study properties of quark gluon plasma matter, which is deconfined strongly interacting QCD matter with color degrees of freedom. And this experiment start data taken since the 2009. We already had 2 long sessions, run 1, run 2, with a long shutdown in the middle. So here you can see table with some overview of the system, colliding system. So we had proton-proton, lead-lead, proton-lead, and just 1 run with the xenon-xenon. But we'll focus only on these 2 systems. As you can see, energies, collision rates, and the names of the luminometers which were involved into these luminosity measurements. And currently we have run 3, which started in 2022. It will continue taking data up to 2025. So nominally, we claimed for PP system energy will be 13.6 teraton volts, for lead 5.36. And with the collision rate nominally for PP, 0.5 megahertz or 1 megahertz, and 50 kilohertz nominally will be taken for the lead. As luminometers, we use FIT system, system of 3 detectors, FZD, FT0, FE0, and for lead we will use FIT and 0-degree colorimeter. A few words about luminometers in round 2. So there were 3 luminometers, T0 with the concept 2 circular arrays of Cherenkov radiators with PMTs, 12 channels per each side, both located on opposite sides with respect to the interaction point. Trigger conditions for proton lead, which were used, is the coincidence between A and C side, at least 1 hit in time range per side with the vertex trigger ranges. FV0 main concept is 2 scintillators arrays, also located on opposite sides with a larger number of channels. For the triggering proton lead, they used coincidence between A and C sides, at least 1 hit in time range per side. And for lead, they used multiplicity trigger. 0-degree colorimeter, 2 sets of identical hadronic colorimeters far from interaction point around 100 meters. Used only for the triggering lead collisions, at least detected 1 neutron. This slide you can see, as you can see, results from the round 2. So we have concluded visible cross-section in proton for both proton luminosity which were used in proton system T0 V0. So it slightly decreased during the time due to aging. Also table with the uncertainties. So maximum uncertainty percentage is up to 2.7 was in total in 2017. At the second part, part of the slide, you can see results from the lead visible cross-section calculations. One need to mention that for 0-degree calorimeter, high visible cross-section value it is large due to the electromagnetic dissociation. So results of an explanation will be presented on Tuesday during this conference by Uliana Dmitrieva. Studies of the electromagnetic dissociation of lead 2008 in ALICE experiment at LHC. So let's continue with the round 3. In round 3, we use 4 luminometers, 3 of them combined into the one system of 4 detectors and ZDC. Some of them are successors from the previous round 2, for instance, FT0, but with a new used mechanism for detection. It contains 2 arrays of Cherenkov radiators, but now we use multi-channel plates and larger number of channels per each side. Trigger conditions for proton-proton is coincidence between A and C side based on the hardware cut of the signal arrival time difference, like OTVX in round 3, also based on our A or C signal. And for LED, 2 amplitude triggers will be used, multiplicity trigger and amplitude with amplitude range, given amplitude range. FDD detector, which is successor of AD detector. One need to mention that AD detector was a forward detector and it haven't been used as luminometer in round 2, and it was used for diffraction physics. It has also, as a concept, 2 scintillator arrays, 2 layers per array, 4 channels, so in total 16 channels at both sides. Same conditions as FT0s. FV0 detector array of scintillators at both sides. So based on the amplitudes. So here you can see trigger conditions for LED, and also ZDC will be used for LED. So system forward detectors' main purpose is to monitor luminosity, background monitoring, production of fast and clean trigger signals, precise collision time for calculation of time of flight, and multiplicity measurements, which contains reaction plane calculation and event centrality. Main feed properties. FT0 is currently taken as main luminometer because it is not sensitive to the particles conduction because of amplitude swoop due to radiators back coverage. It is not triggered by satellites for luminosity, beam colliding bunches. It's taken for monitoring. For background monitoring, we use FT0 by using non-colliding information about non-colliding events in non-colliding bunches with a non-beam bunch mask, and FDD FV0 uses early arrival time. So as you can see, this slide presented vertex versus collision time without no cuts. You can see as FT0 C position, FT0 A position. So time-based FT0 vertex trigger logic contains first time trigger signal RA and RC production, which is based on the averaged time taken from channels, which satisfies hardware time cut. Currently, it's configured ±2 nanoseconds, and hardware vertex position measurement, which is difference of RA and C times, and vertex signal will be produced if hardware vertex position within the range, given range, which is also configurable parameter. Such vertex trigger signal concept allows to remove satellites events in offline and, of course, online, which is important. At this slide, you can see distribution of the events of the trigger signal per each session within 2022 and 2023. Fraction of the trigger signals with a beam mask, which occurs in a collision, and with respect divided by any BC mask, which means without any cut. So FT0 detector front-end electronics architecture, its concept allows to see events with exact bunch cross identification. identifier. With such feature, we can identify with the full efficiency each BC and remove ghosts, which is non-beam mask. Sessions during 2022 and 2023 showed less than 0.6 outliers, as you can see here. And this means that we have perfect DOS-BC event rejection. So, and the last point that FT0 vertex reconstruction shows good perfect correlation between primary vertex used by using data from tracking detector. It shows perfect correlation. Also, hardware trigger within the range plus minus 20 centimeters is good signal for registering collisions and monitoring luminosity. Also, FT0 has best time among time resolution among all feed detectors, which is 70 picoseconds. The last status about one scan. So we had one scan in November 2022. During that scan, we collected data by using feed detectors, luminometers, and tracking inner tracking system. Also, we collect information about beam property by using independent LHC tools. As you can see here, 4 stages, each one. As a summary, I'd like to mention first measured visible cross-section provided and its uncertainties during Vandermeer scans in round 2 for PP and lead-lead collision systems. Main is luminometers for PP sessions. In round 2, it was T0 and V0. In round 3, it will be FT0 because of the background suppression for backward direction. Satellite rejection, ghost bunch rejection. Also, the scan analysis for round 3 is currently ongoing, and FT0 shows good performance, good correlation between vertices, primary and FT0s, and precise collision time for TOF-based particle quantification. So thank you for attention. Also here I put some links and QR code for the recent video, which we created recently at LHC at CERN. Thank you.
Thank you very much. Please, questions?
Thank you for the nice presentation. If I remember well, the total uncertainty of luminosity determination in round 2 was something like 2.2 or 2.3%. Could you please explain whether you expect a better systematic uncertainty with round 3? But this is round 2, right?
Yeah, this is round 2.
But yes, okay. Maybe I'm wrong, but what about round 3? What is the number for round 3? Expected number, and since you actually use a brand new detector, what it will be done better?
So currently, because analysis is ongoing, I cannot estimate uncertainties in round 3 because for now we have quite new system, and this requires investigations on some features which we have currently in round 3. So I cannot estimate uncertainties in round 3. So we have to wait for results, unfortunately.
Okay, thank you.
Questions from our side? Okay, thank you very much. Next speaker, Evgeny E.Kryshen, Kurchatov Institute, overview of recent ELIS results. So please.
I hope everyone can hear me. Thank you very much to the organizers for this opportunity to present ELIS results. I will start with a brief advertisement. Recently, we've published a review paper, 200 pages, where we tried to summarize all ELIS results from run 1 and run 2 and tried to wrap up the properties of quark gluon plasma in heavy ion collisions, in particular macroscopic properties, properties of partons traveling through this medium, and touched various aspects such as initial state and hadronization. We also looked into QGP-like effects in small systems and many other aspects of QCD physics and beyond. And I will not touch all the aspects here, and I will concentrate on heavy ions, while Yuri Harlov will discuss small systems and the QCD aspects on Tuesday in more detail. Let me start with this nice sketch where one can see the evolution of these little bangs we produce in heavy ion collisions. We start from the collision of two contracted nuclei, and then quickly it equilibrates, and a quark gluon system or medium is created with at a time scale of about 1 Fermi over C. Then this QGP medium is expanded, and at some point it converts into hadrons, and then these hadrons go to our detector, and this is what we see in ELIS. And the goal of our experiment is to deduce the properties of this medium we create by looking into the final state observables. And of course, we have different probes ranging from soft probes to hard probes. And we have a nice tool, the ELIS detector. I will not go into details of various components. Let me just briefly emphasize that we have two major features that allow us to perform these measurements. The first one is the broad momentum acceptance. That allows us to study various properties from soft to hard scales, and the world-leading particle identification capabilities from energy loss measurements in TPC, from time of flight, and other tools. And here you can see a nice sketch where we show various particle species we can measure either with decays, with calorimetry, or with PID techniques, and the range of PT which we cover with these observables. So let's go to the results, and I will start with global properties of the produced medium. And the most simplest observable is the charged particle multiplicity per participant, which is shown here for lead-lead collisions and for proton-proton collisions, and as function of energy. And one can see that the trend in lead-lead collisions is clearly different from PP, so we can conclude that the heavy ion collision is not just a superposition of nucleon collisions. And we can go further and try to deduce initial energy density from the observed multiplicity and transverse energy. And this is what we've done as function of number of participants. And here you can see a summary. And for the central collisions, the observed initial energy, the deduced initial energy density is factor 30 higher than the energy density which is predicted from the lattice QCD. And of course, one would expect that the temperature of the produced medium is also very high. And this is what we confirmed when looking into the spectrum of direct photons. And when we do it, we can measure the slope of this spectrum and basically extract the effective temperature of the collisions, which appear to be about 300 MeV. And this is twice larger than the temperature of the transition to the quark gluon plasma state predicted by lattice QCD. So we study a really hot matter. We can go further and study particle spectra. And here you can see an example of particle spectra for PT spectra for different particle species for central and peripheral collisions, and one can already see that these spectra are very different. So something is going on in central collisions. We can go further and integrate the spectra for central collisions and extract total yields at mid rapidity. And here you can see our final results where we plot the yields at mid rapidity for different particle species, I think 21, here ranging from pions, which are most abundant, to helium-4 and anti-helium-4, basically ranging by 9 orders of magnitude. And a remarkable feature is that we can fit all these yields by a very simple statistical hadronization model, which is based on the fact that the produced hadrons, they are produced on the phase boundary, and they are driven by statistical laws. And using this model with just 2-3 parameters, we are able to fit all these yields, which are ranged by 9 orders of magnitude. And when we do this fit, we can extract the temperature of chemical freeze-out. And this temperature of chemical freeze-out appears to be close to the phase transition temperature of about 160 MeV, as predicted by lattice QCD. So we get another confirmation that what we see was really hot, and it thermalized at this temperature. We can go deeper into this temperature business and try to study germanium states. And germanium was predicted as a signature for the quark gluon phase transition 30 years ago or so. And the idea is that germanium is expected to melt due to color screening effects in QGP. And that allow the suppression of the germanium was indeed observed at low collision energies, seen here, for example, for Na60. This is a ray factor, basically suppression as function of charge particle multiplicity or centrality, if you want. And of course, we expected the same trend in at higher energies, but later it was understood that another effect may play a role, so-called regeneration of germanium due to high multiplicity of CC bar pairs produced in the collision, about 50 pairs per central collision. So we have a high probability that they interact and produce germanium bound state. What is it? And indeed, this is what was observed. Going from low energies to high energies, we see that the suppression pattern is such that it fades away. And indeed, so this is a clear signal of regeneration effects. We can go further and look into PT distributions of this array. And what we find is that this factor, this suppression is smaller at low PT. And this is the effect which is also expected in the regeneration scenario, because most of the CC bar pairs which are produced, they are produced at low PT. And of course, when we look into central collisions, into the mid rapidity suppression factor, we see that it is even higher. This is because at mid rapidity we have much higher statistics of CC bar. We can go even further and look into excited germanium states or quarkonium states. And this is even more interesting because different germanium states, they are expected to melt at different energies. They have different binding energies, and loosely bound states, they melt first. And indeed, this suppression, sequential suppression, can be used as an effective thermometer of the QGP. Because, for example, psi1s is the most bound state. It is expected to melt the last. While, for example, upsilon3s is melting the first. And indeed, this pattern was observed. I have to admit that it was first observed by CMS. They checked the suppression factor for upsilon1s and upsilon2s, and one can clearly see that for 2s, the suppression is much higher. And with ELIS, we were able to extend this CMS measurement towards forward rapidities. And what we did new is that we looked into the charmonium sector and looked into Psi2S suppression, and indeed what we see is that Psi2S is suppressed much larger compared to JPSI. And the same pattern for PT. If we look into the PT distribution of this suppression pattern, then we see that charmonium is, Psi2S is also showing a signal of regeneration effects at low PT. So there is some new feature in this game. After this rapid expansion of the QGP, we go to the hadronic phase, and resonances, short-lived resonances like ρ0, K star, or lambda star allow us to probe the properties of this hadronic phase. The point is that when we look into the yields of these resonances with respect to their counterparts as function of multiplicity or centrality, we find that the yields of these resonances, they tend to decrease with respect to the yields of their counterparts. And this is explained by the fact that in the hadronic phase, these short-lived resonances interact with the matter, with the hadronic matter, and in addition, they tend to decay, and their lifetime is consistent with the lifetime of the hadronic phase. So we can use this pattern to extract the duration of this hadronic phase. And people tried to extract the hadronic phase duration and found that depending on the hadron we take, depending on the ρ0, K star, or lambda star, we find different hadronic phase durations ranging from 1 to 10 femtometers OC. And of course, it is a puzzle, and we can conclude mainly that there is no clear picture now on the hadronic phase duration, and it might happen that this hadronic phase is very complex, and different states, they go to chemical freeze out at different times. So this is to be studied further. And let me show this last picture on the temperature. We try to summarize all observables which are related to the measurement of the temperature of the collisions. And here you can see, for example, the temperature which we extracted from the suppression of upsilon2s and upsilon1s, corresponding to about 600 MeV. Then effective temperature extracted from direct photons of the order of 300 MeV, then going to chemical freeze out about 150. So all these observables allow us to construct a really nice and consistent picture. Now let's go to the next topic, the anisotropic flow. If we consider non-central collisions, we should expect the following effect. We have a non-uniform and asymmetrical shape in the initial state, and during the expansion of the medium, this anisotropy of the initial state translates into the anisotropy in the momentum space, and we usually do the following. We fit these angle distributions with Fourier decomposition and extract the so-called VN coefficients corresponding to these Fourier coefficients of this decomposition. And we study these coefficients as functions of centrality and PT and so on. Here, let me just summarize the main outcome of these studies. Here you can see different flow coefficients ranging from V2 to V4, and as function of centrality for different particle species. Also, we show this average PT corresponding to the radial expansion, and I hope you can see that these measurements, they are approximated with the hadronic models, and these hadronic models are able to describe the measurement very nicely. And one of the parameters of these models is a so-called shear viscosity to entropy ratio. And out of these measurements, we could extract the E/RAS ratio, the ratio of shear viscosity to the entropy. And it appeared that this parameter is very close to the ADS CFT limit, and basically we observe very small parameter corresponding to the strongly coupled quark gluon plasma. So this came up as a surprise because initially it was thought that KGP should be considered as a gas of freely flying quarks and gluons, but this is not the case, at least at LHC energies. Then we can go further and study hard probes. The point is that one of the hard probes is jet. Jet is produced from the parton, and if this parton is produced in the initial state, then it transfers. Then it passes through the medium, and the energy loss of this parton translates into the energy loss of the jet. And what we see is that the nuclear suppression factor for jets in lead-lead collisions as function of PT shows a very strong suppression, so up to factor 6-7 at relatively low PT. And it is I must admit that this is an exercise where all experiments at the LHC contributed. Here you can see Atlas and CMS results at high PT, where Alice is not able to do the measurement. But I would say that the picture is complementary, and we do a nice job here. This suppression factor was fit by different models, and we were able to extract the number, the energy loss, the average energy loss per the parton of about 8 ± 2 GeV, dominated by the radiative emission. And now we are developing new machine learning techniques that allow us to extend the measurements to lower PT and to larger jet radii. I remind you that standard jet radius, which is considered, is 0.4 in angle, and we managed to do it to 0.6 and rule out several models due to that. We also do various jet substructure studies. Of course, we expect that the shape of the jet when the parton travels through the medium should change, and we can study various subtle effects of jet shapes. And here I just give one latest example where we tried to plot so-called delta R distribution corresponding to the angle between standard jet axis used in the anti-KT algorithm for the jet reconstruction and the so-called winner takes all axis, which is often consistent with a leading particle. And if we plot such a distribution for lead-lead collisions and proton-proton collisions, we see that for lead the distribution is narrower, and this means in particular that quark-initiated jets are more likely than gluon-initiated jets. And we also managed to roll out some of the models here. We have also nice results on heavy flavors. Heavy flavors also provide us a hard probe and for all PTs, because the hard scale is provided by the heavy quark mass. And from experimental point of view, the achievement is that we managed to measure the array factor down to 0 in PT, and this is a challenge because we have high combinatorial background in this region. And here I just provide two results where you see nuclear suppression factor for charm mesons and the V2. And initially it was a challenge for these charm quark models to simultaneously reproduce the array, the nuclear suppression factor, and the elliptic flow measurement. But now, since after several years of detailed studies, theoretical curves nicely lie on the measurements, and this allowed us to provide constraints on the heavy quark spatial diffusion coefficient, and you see the number here. And this is at the moment our achievement. I would say the range is quite high at the end. I would also mention that we observe a nice pattern when we compare non-prompt and prompt D0 decays. Non-prompt Ds come from the Batamonio, from B-meson decays, and this means that this indicates that there are mass-dependent energy losses in agreement with expectations from QCD, because heavier quarks, they are expected to interact less with the medium compared to C quarks. And what you see here is that we have high uncertainties in this, for example, this band here. And this is mainly due to the fact that our initial state is not well constrained. And indeed, we expect a high shadowing effects, or large shadowing effects of in LED initial state. And hopefully we have a tool to study this effect in more detail with ultra-peripheral collisions. So these collisions correspond to the fact to the case when we have two colliding ions interacting at impact parameters larger than 2 nuclear radii, and in this case hadronic interactions are suppressed, and we are left with photon-induced interactions. And the most interesting is the photoproduction of gypsy on a nucleus. And the reason is that this cross-section for this process is proportional to the squared gluon density in the target, so we can study the gluon density and the link with this process. Recently, we've managed to measure the cross-section for the photon, for the production of gypsy in photon LED interactions as function of photon LED energy, down up to very high energies corresponding to Bjork NX of the order of 10 to minus 5. And we see that this cross-section is suppressed with respect to the impulse approximation, where the shadowing effects are ignored. And if we build the ratio of this measurement to the impulse approximation, we see a clear suppression factor pattern, and we can extract the gluon shadowing factor of the order of 0.5 at x values as low as 10 to minus 5. And this is an achievement because if you take recent parameterizations, gluon density in this region is practically unconstrained. So using this data, we will be able to improve our models and understanding of the quark gluon plasma. Okay. I will probably skip this another example of ultra-peripheral collision measurements because I have not enough time, and go to our future. And the future is that we successfully upgraded our detector and switched to continuous readout. And the idea is that we will collect a huge statistics of minimum bias events, a factor 100 larger than what we had in run 1 and run 2, thanks to this continuous readout and high rates. And we've already started collecting this data in proton-proton collisions. Here you can see a pattern of our delivered and recorded luminosity. We're taking data at proton-proton collision rate of about 500 kilohertz, corresponding to quite low mu value. And this is our roughly 0.02. And this is the difference with respect to CMS, ATLAS, or LHCb experiments. So we can measure various observables at very small pileup. And what we do, we first collect all the data and store it on tape, on disk, and then we have several months to process this data to perform offline selection. And at the end, the plan is to store only 10 to minus 4 of the selected time frames. And here you can see a nice performance of our PIT, both with TPC and time of flight. A nice charm measurement. This is D0, I think, and already now we got a factor 100 more statistics for these. That wasn't possible with triggered readout, and we see a nice first signal of anti-helium-4. You can imagine that it is very difficult to produce light nuclei out of proton-proton collisions. And hopefully we had a chance to taste a smell of LED collisions in November last year, and here you can see a nice event display we got from that. We managed to collect only small sample, about 1 million of events, but now we are extensively checking what is going on and use it to improve our understanding of our brand new detector. We have future plans, nice future plans. First, we are going to install the new inner tracking system in run 4 and also the focal detector to measure photons in the forward direction. And at the end, after LS4, we are going to replace our detector with a brand new detector based on the silicon technologies, so-called LS3. And I give here some links where you can follow the developments. And let me go to my conclusions. We've collected a wealth of physics results from run 1 and run 2, and we switched from qualitative statements to quantitative understanding of what is going on there. We measured the temperature, the transport coefficient, the energy loss, and other aspects of QGP physics, and performed a successful upgrade of our detector. Now we are running our detector at full speed with continuous readout, and looking forward to the new LED data, which is expected, I think, in September this year. With this, I just want to welcome you to read our nice race review paper and go through the journey through QCD with us. Thank you very much.
Thank you for this nice review. Please, questions.
Does the list measure net baryon probability distribution, or at least net proton probability distribution in addition to cumulants of this distribution?
Yes, I think we have such measurements, but I have no slides on that. Sorry. No slides on that.
And concern to your slides, will this measure double JPSI production in the future?
Well, I think it should be possible, but I don't remember whether we had some performance plots or some projections on that. Sorry. I think statistics should be enough to do that.
Can I ask a question?
Please, question from outside.
Yes, I have a question. This is Sergey Petrushenko, Moscow State University, and also CMS. This is about slide number 8. Could you please show it? It's about eta dependencies about RA.
This one?
Yes. Could you please comment somehow the comparison of your and CMS data with hydrodynamical models for eta dependencies of these excited quarkonium states?
Sorry, you say how these measurements are compared?
Yes, because I see something interesting in high eta region.
Okay, I see what you mean. That yeah, at high rapidity we have a increasing trend of this array. This is probably because at forward rapidity we have less density, and the suppression pattern is less pronounced. But you mean that?
Yeah, I mean the comparison with hydrodynamics, because hydrodynamics predict a little bit another dependencies for at least first state of epsilon.
Within these uncertainties which we have here, it is difficult to prove that there is a difference, but we hope to get better results in round 3.
Yes. Okay. Thank you. Okay. Thank you.
More questions from outside? Okay. Thank you very much. D.Baigarashev, Dubna, latest results and precision measurements from the NA62 experiment.
So good morning. My name is D.Baigarashev, and I want to say organizing committee for the interest in the NA62 collaboration results. Today is my talk about latest result and precision measurements from the NA62. And I would like to say about measurement of the ultra-ray count decay to the pi nu, and also precision measurements of the other ray decays, such as pi mu and count decay to the pi and to photons. Also searches for lepton flavor violating and lepton number violating processes, and shortly we have preliminary result for dark photon searches. So shortly, briefly remind about NA62, and NA62 experimental hole located in the north area of the CERN CPS, and it's a high precision fixed target count experiment, and the main goal of this experiment is to measure ultra-ray count decay to the pi nu bar, and also have a broad physics program. And 15 years ago, NA62 was approved in the CERN, and from 2016 to 2018 was run 1 data taking, and from 2021 we have ongoing run 2 data taking. 400 GeV protons from CPS used to produce secondary hadronic beam, and only 6% of this beam is count component. And in NA62 used 2 trackers. First of all, it's GTK in the upstream region from, and other one is big straw chambers placed in the vacuum tank. And for the main analysis, for the analysis, we are using count decays that decayed only in the fiducial volume from Chanty to first straw chamber. It's this from Chanty to first straw chamber. So measurement of the ultra-ray count decay. Pi nu, it's a golden decay mode in the count sector. SD transition sensitive to CKM structure of the standard model. It's a theoretical clean process dominated by short distance physics and sensitive to new physics in the lepton sector as well. And pi nu, it's extremely rare process in the standard model with 10% precision. For the analysis, we are using 2-dimensional plot with pi plus momentum on x-axis and squared missing mass on y-axis. Here you can see 2 bands from muon neutrino decay, and second one is from pi plus pi 0 decay. And for the pi nu search, we define two regions with several control regions kept close to the signal regions, and control regions opened first to validate background expectations, and after that we can open signal regions. So here you can see this plot with 2018 data. Here, after combining the complete run 1 data taking, we observed 20 events in the signal region and measured branching fraction from 20 events. You can see here we at 68% confidence level. It's more than standard model precision, but we are working on improving this result in run 2 data taking. Precision measurement of the other decays. Pi mu decay heavily suppressed. It's also SDD transition with lepton pair in the final state. This decay described in the scope of chiral perturbation theory and mediated by 1 photon exchange. Main goals for this decay in the NA62 are model independent measurement of the branching fraction for this decay, measurement of the function W from Z, determine the form factors A plus and B plus, and forward-backward asymmetry. After the signal selection, we observed more than 27,000 events with 8 events expected as background. In this plot, you can see reconstructed mass of pi mu with good agreement to data to Monte Carlo. Here I show main results for this decay. We improved branching fraction from previous results, A plus B plus form factors, and also new result for this year, it's forward-backward asymmetry with 90% confidence level in upper limit. For the next decay, this decay allows chiral perturbation tests at high level. And main background for this decay is cluster merging in the electromagnetic calorimeter. And after signal selection, we observed more than 4,000 events with more than 400 expected events as background. Here I show only some results, preliminary results with branching and real parameter C. What about search for lepton, flavor, and lepton number violating? Violating of lepton number and flavor violate conservation laws predicted in BSM models. For the NA62, we studied several channels, and our key points are its tracking resolution and particle identification. Here is listed some results with improvements in upper limits and 2 new results for decays, pi minus pi 0, 2 electrons, and muon neutrino and 2 electrons, positrons. And last result in dark search based on 2021 data. For the NA62, it's easily to change between cone regime and beam dump mode. We need just to change to cuprum-ferrium collimators. They use it as a target. And for the search dark photon production in interaction with taxes, we collected 1.4 times to 1070 protons on target in 2 days and observed 1 event with 2.4 sigma significance. Here many results from run 2 and first results from run 1 and run 2. And last one, it's our plans for the future. High intensity cone experiments under discussion at CERN. To measure other golden decay mode, K long, and other dark sector searches. Thank you for the attention.
Please, question from outside.
Sergey?
Okay, do you hear me?
Yes.
Okay, which model for the dark photon has been used for interpretation of your results?
You mean this one?
Yeah.
In the vector sector, dark photon, so we are using protons that product that have interaction with target in nucleus, cuprum and ferrum, and the final state. Yeah.
No, I mean theoretical model. How you extend the standard model to obtain the dark photon?
So it's beyond standard model.
Yeah. Which kind of model? Also, this should be some type of the some abelian extension of the standard model gauge group.
Я понял, да, вопрос. I think I cannot answer for now.
Okay, thank you.
Please, more questions from outside. Okay, let's maybe. Next talk, J.Milosevic. Jovan, do you hear me?
Yes, I can hear you.
Very nice.
Can I share my screen?
Nuclear Science. The title of the talk is Highlights from Quark Gluon Plasma Studies in Relativistic Nuclear Collisions. Please.
Can you see it? Hello?
Yeah, we can see it, everything is okay.
Okay. Good morning. So I'll try to give some highlights from quark gluon plasma investigation. So it has been shown that in relativistic heavy ion collision, a drop of quark gluon plasma, QGP, can be formed. Physics in heavy ion collisions ranges from rare, highly energetic partons that can be described with the perturbative quantum chromodynamics up to above of low energetic partons that form the QGP. Highly energetic partons travel through the QGP and interact with it. At the end, they end as a spray of particles that are called jets. The aim of producing the QGP is to study its properties. It can be done by analyzing the final particles. Two main observables to perform it is to study collectivity and nuclear modification factor. In both, the initial state fluctuations play a very important role, and I will mainly speak about that. I will have time to show a small part of these things, and I'd like to stress the dependence of the initial state, the incident energy, and of the system size. And at the end, I'll show that despite the completely different underlying physics, that there are anisotropies even in ultra cold gases. So as the colliding nuclei are accelerated up to ultra-relativistic velocities, the collision that happens is in fact a collision of Lorentz contracted disks with thickness of RA of gamma. The thickness depends on the velocity. Each of these two disks has many colored partons. But the density of these is not uniform. Due to the huge velocity, incident partons interact softly. After such a collision between these two disks, longitudinal color fields are produced. As the longitudinal length of these fields enlarge, the QQ bar pairs are produced. So with time, these fields decay into gluons and QQ bar pairs. On the other side, a very small fraction of the incident partons suffer hard perturbative interaction, and they will produce particles with high transverse momentum, PT. During the expansion, its density decreases. The viscosity to entropy density of the system is very low, close to the quantum level. A strongly coupled quantum system that consists of low PT partons forms a collective system that is expanding as a relativistic fluid with a very low shear viscosity over the entropy density ratio, eta S. Initially, the transverse velocity is very small, but due to the pressure-driven hydrodynamic expansion, it rapidly increases up to about half of the speed of the light. Initially, a non-central collision overlap region looks roughly as a lens. So it seems that there should be a reflection symmetry, but due to the lumpiness in the energy density, that symmetry is broken. Even in a most central collision, such an initial state will break reflection symmetry. One of most important thing in heavy ion collisions is to study temperature baryochemical phase diagram. Experimentally, it is or it will soon be accessible at high LHC and low Nika energies, respectively. The question is what type of transition between the QCD partonic system and hadronic system is a critical point. Earlier mentioned high energy partons while passing through the QGP evolve, decay, and finally produce a cone-shaped spray of hadrons that we call jets. Jets are quenched in the QGP. There is a strong interaction between jets and liquid QGP. So a huge loss of initial high energy partons means that the system is strongly coupled. So in contrast to proton-proton collisions where jets are also produced, jets produced in nucleus collisions are strongly quenched. In studying it, the path length of the produced jets has a big importance for the amount of jet suppression. So studying of jets is not decoupled from the azimuthal anisotropy. Also, one can study suppression of different parton flavors in order to investigate the strongly coupled QGP. 20 years ago, people had an imagination of two nuclei in the transverse plane to be presented as two cycles that overlap. Thus, naturally, the reflection signal appeared. If we connect the centers of these ideal cycles, we'll get so-called impact parameter vector. Its magnitude depends on the centrality and goes from 0 to 2r, where r is the radius of colliding nuclei. At that time, people thought that only elliptic flow can exist. Later on, we realized that it is not the case, but there are also non-zero higher order Fourier harmonics. It has been a puzzle for some years. Then we realized that it is wrong to imagine nuclei to be a sphere with a homogeneous distribution of nuclear matter in it. In fact, it consists of nucleons that are not so densely packed and can move. Due to the fluctuations in position of nucleons, the density of nuclear matter is not homogeneous. Different densities means different pressure in different directions, and thus different magnitudes for the Fourier harmonics. So higher order of Fourier harmonics will appear, and we saw them, and we can measure them. Here again, I am showing that idealized picture of a collision of two nuclei. The reaction plane is formed from the impact parameter vector and the beam z-axis. Usually it is denoted in that way. So in this picture, the reaction plane spans over the x and z axis. One can make a distribution of the azimuthal angles phi of the emitted particles with respect to the reaction plane and make a Fourier decomposition of it. Due to the reflection symmetry, all sign terms will vanish. The Vn coefficients are used to quantify magnitude of the anisotropies. We know that Vn depends on the global geometry of the collision of the initial states and the transport properties of the QGP. Nowadays, we know that, in fact, reaction plane does not exist. Thus, we use so-called event plane that is determined by the beam direction and the direction of the maximum density of the outgoing particles for each Fourier order separately. The nuclear modification factor is used to study jet quenching. It is normalized ratio of the PT distribution in nucleus, and proton-proton collisions. If RAA is equal to 1, that means that there are neither hot nor cold effects. If it is smaller than 1, then there is a quenching. Here is an example how the initial state fluctuations influence on the anisotropies in ultracentral lead-lead collisions at the LHC energy. If there would be present symmetry of the global initial geometry, then all Fourier harmonics would equal to 0. In the plot are drawn magnitudes of different order harmonics, elliptic, triangular, quadruple, and even higher orders. Different symbols corresponds to different centralities. We see that there are no zero, they are not equal to 0, and that they saturate at some final values going to the most central collisions. Beside it, we could see so-called also factorization breaking both in PT and pseudo-rapidity direction. All of these appear due to the initial state fluctuations. So these event-by-event fluctuations have a strong influence on the anisotropies and can give an insight into the early state dynamics. We also know that a proper description of the initial state is extremely important in comparison between the model and the data. It is also known that fluctuations of the elliptic flow, for example, are not Gaussian. Thus, it is important to precisely measure these non-Gaussianities in order to test hydrodynamics and constraint models of the initial state. Non-Gaussianities are quantified through skewness, kurtosis, and possibly higher order moments, and they are present in the early stage of the collision. They are probably partly washed out during the subsequent expansion of the form system, but their traces could survive. Their measurements can provide some constraints on the theoretical models. Q-cumulant method is based on the Q vector. One can derive 2, 4, 6, and higher number particle correlators, and from them to reconstruct the corresponding V2 values. The advantage of the cumulant method is that it can remove non-flow correlations and to reveal the splitting between the cumulants of different orders. These can be used to reconstruct the central moments of the V2 distribution. Disadvantage of the cumulant method is that with an increase of the cumulant order, the formulas become quite complicated. Also, in order to have a good feasibility of the cumulant method, one needs a big enough multiplicity per event and a big enough VN magnitude. Based on the cumulants up to the 8th order, Olitro proposed such a hydrodynamic probe. One can make a Taylor expansion of the V2 generating function. If one restricts expansion in only first 3 moments, so mean V2, its variance, and the skewness, then the left side of this equation will be equal to the number 1/11. So it should be independent on centrality. Alice and CMS performed the measurements, but the precision was not quite satisfactory. So for the first time, the V2 from 10th order cumulant is measured and used to perform hydroprobes and to measure central moments of the V2 distribution. Due to non-zero flow variance, there is a gap between the V22 and higher order cumulants, V22K. Cumulants are measured within the so-called hydro regime, so up to 3 GeV per C in PT. If one takes into account higher order central moments like kurtosis and superskewness, then one obtains such expression, and the hydro probe becomes centrality dependent. Also, employing the cumulant of the 10th order, V210, one can construct a new hydrodynamic probe, that second one. Again, if in the expansion one would restrict up to the skewness, then this second probe would be equal to the number 3/19 and will be centrality independent. With closed blue cycles is shown the first probe. One see that in fact it is centrality dependent and that deviates from number 1/11. With closed red squares is shown the second probe. It is also centrality dependent and deviates from number 3/19. With corresponding open symbols are shown distributions that corresponds to the expressions obtained from the Taylor expansion of V2 generating function that is not limited to the skewness, but includes also kurtosis and superskewness. One can see a very good agreement between the left and right-handed sides. So this proves that the higher order moments of the V2 distributions are not zero and that they are necessary to describe the data. So at high LHC energies, it appears that these two distributions in fact are centrality dependent. That is question, of course, so how it will look like at smaller, for example, Nika energies. One can also measure cumulants, to use measured cumulants in order to measure moments of the V2 distribution. An approach given by Letroy is adopted to measure standardized moments. Besides the skewness and kurtosis, one can construct super skewness. The problem is that each standardized moment has some small contribution from other moments. Again, using the Taylor expansion, one could, to say, clean them from these contributions, and such moments could be called corrected moments, and they are also expressed through the measured cumulants, but their formulas are much more complicated. As an example, here is given expression for the corrected corrected skewness. In previous measurements, Atlas and CMS have been measured standardized skewness. It is plotted down in paper, using the CMS data extracted kurtosis. But again, so the trends are visible, but the statistical uncertainties are still rather big. Based on a huge CMS statistics, 2 billion 2 times 10 to the 9th events. Here are shown the CMS results on skewness, kurtosis, and super skewness. With closed symbols are shown standardized, and with open ones, the values of corrected moments. Both standardized and the moments have similar shape, but differs a bit in magnitudes. The slope of the corrected skewness and kurtosis is stronger than for the standardized one. These results can be used by theoreticians to tune the initial conditions such to reproduce experimentally measured moments of the V2 distributions. This slide is used to show feasibility of the Q cumulants at lower Nika energies. The statistics is small, 34 million minimum bias events, so it is nearly 100 times smaller with respect to the CMS data. But even with such a small statistics, small V2 magnitudes and relatively small multiplicity, the V22K values can be measured. With the real data, that should be about 10 to the 9 minimum bias events per year, the statistical uncertainties will be for one order of magnitude smaller. Thus, we can expect that the V22K values can be measured up to centralities, maybe 35 or maybe even 40%. Intentionally only charged pions are used in difference of protons that could be just wounded original protons from the colliding nuclei. Charged pions are newly formed particles that could be produced from quarks if QCD matter will be formed. Also, we restricted it to the TPC, MPD TPC acceptance and PT and pseudo rapidity. The model, as expected, gives that gap between the V22 and higher order cumulants between the higher order cumulants, the V24 is measured the best. So that is fitted with polynomial of the third order to use it for the elliptic power distribution. That distribution depends on 3 parameters: the number of sources and the ellipticity, epsilon nulla. The K parameter relates linearly the calculated initial eccentricity and elliptic flow magnitude. And it is chosen such a way so to imitate the V2 obtained from the model at the top Nika energy. For this third order polynomial is used for fitting the V24, but because the model statistics is small, that can cause not good enough V24 positioning, and thus consequently the V22 and as well as the higher order cumulants, and that can break splitting between them, and in that way so to make impossible so to measure central moments of the V2 distributions at small Nika energies. So we think so that because Nika is much lower energies, so that maybe initial fluctuations are not so much exposed as at the highest LHC energies, and maybe that will cause washing out, the higher order central moments like kurtosis and super-skewness, and maybe only skewness will survive. But of course, without the real data, we cannot say so what can happen. So on this slide, we show that theoretically predicted results on hydroprobes using the Trento calculated alpha and epsilon 0 parameters. And on the same plot are also given CMS data. These Trento parameters give a rather similar shape and even the magnitudes of the hydroprobes. But one should stress here that Trento is prepared for higher RIC and LHC energies. So that could be an explanation of the scene similarity. But it is question so how it will look like at the Nika energies. Here are shown the results of the skewness at Nika top energy calculated from the corresponding V2K cumulants. At the same plot, again, is shown the CMS results. The MPD skewness shows an expected sign. The absolute magnitude is bigger than 1 from the measured from the CMS data. Here one should stress the two potential problems. The skewness is obtained using the elliptic power distribution that is calculated using the previously mentioned Trento parameters. At the moment, we do not know so how reliable they are. Another problem is because of the fit of V2.4 or using very small statistics maybe is not good enough. So with the real data, we will see exactly so how it will look like. I would like to show some results from the experimental data at low collision energy. So it is top SPS energy. These are Ceres data. The V2 and V3 are measured in rather central collisions. Ideal hydrodynamics predicts that if the formed system is partonic and behave according to relativistic hydrodynamics, then the ratio V3 power 1/3 divided with V2 power 1/2 should not depend on PT. So here I'm showing the result. For PT above 0.5 GeV per C, this ratio is rather PT independent. For the comparison on the same plot are shown the corresponding LHC, Atlas, and Alice results. There is a rather good agreement. For the Ceres data, the ratio increases its magnitude at small PT because HBT contribution in the V3 is probably not completely removed using the Olitro procedure for removing the HBT contribution. Here is also comparison between the Ceres data and the VHLLE model. VHLLE overpredicts the V2, and because of that, underpredicts this ratio. Now I'll move to the nuclear modification factor. Are shown the LHC and RIC results on RAA versus PT. The strongest suppression is seen at about 10 GeV per C. Also going to very high PT at mid rapidity, one sees that RA approaches 1. One should notice that due to the energy loss, there is a migration to lower PT. At small PT, there is a collision energy dependence. As expected, photons do not show any suppression. The RA also depends on the flavor. The latest flavors are most suppressed, as expected. As the mass of the flavor increases, the suppression is becomes smaller. As expected, in the case of heavy flavors, the statistical uncertainty is increased going to small PT. Also, as one can expect, the system size have a big influence on the RAA. If the system size is smaller, the suppression becomes smaller too. Centrality dependency is, in fact, the system size dependence. The migration in PT makes nuclear modification factor is even above 1 in more peripheral collisions. At the end, I would like to show you that the anisotropic expansion in ultra-cold gases is very similar to the one seen in the heavy ion collisions, although the underlying physics is completely different. For example, one can trap lithium atoms using the lasers and the magnetic fields into it looks like a needle trap. And after a sudden release, of these atoms, these ultra cold atoms from that trap, they will expand radially, and they will produce an elliptic flow with a huge magnitude. So again, we have kind of a similar process like in heavy ion collisions. So that initial special anisotropy. Here we see so that aspect ratio in the X and Z direction is huge, so that it will drastically change when because of the expansion in the radial direction, because of and that expansion is pressure driven. So it will transform into elliptic flow seen in the momentum space. So studies of azimuthal anisotropies and jets are consistent with the interpretation that the two Lorentz contracted nuclei in its collisions form a cylindrical volume of the liquid quark gluon plasma. Non-uniform energy density and temperature that appears due to the lumpiness structure of the colliding nuclei have a big influence on the subsegment azimuthal anisotropies and jets. QGP expands anisotropically, and during the expansion, it cools. It can be well described within the relativistic hydrodynamics with a remarkably small specific velocity. Concerning the jets, they have a rapid loss of energy while they are traveling through the QGP. For a system formed with a biochemical potential close to zero when the temperature is about 155 MeV, the system goes through a crossover phase transition and hadronizes. The produced hadrons continue to expand and cool, and when the temperature is about 95 MeV, then so-called thermal freeze-out happens. The produced hadrons remember that anisotropic flow from the QGP, and using them as a final particles that are detected, we can reconstruct flow from the QGP. A similar anisotropic flow is seen in different system sizes and different collision energies. Even more such an anisotropy is seen even in the expansion of the ultra-cold gases too. Thank you. I cannot hear you. Hello?
Yeah, do you hear me?
Ah, now I can hear.
Yeah, yes. Question from the presence. Please.
Cumulants for which distributions did you consider? For distributions in which variable?
These are cumulants in azimuthal angle, so it is the only quantity which is used, and it is made from charged particles in the acceptance that I show in the CMS data. So the only quantity, measurable quantity, is the azimuthal angle.
Okay. No more here. Please, questions from outside. No. Then final, very general question, Jovan. In CMS and Atlas field theoretical model studies, there is these sort of studies are also accompanied by so-called theoretical uncertainty, which makes sense because there we have a number of fundamental constants and the results are model dependent. In heavy ion case, do you have an analysis of theoretical uncertainty in analogy with that field theoretic issues?
At the moment, not, but we noticed that I mentioned that V2 distributions are not Gaussian. There were different attempts to describe them, and many models agree when you look for rather central or semi-central collisions, but when you move to rather peripheral, when I say rather peripheral here, I think for example, centralities between 40 and 60% centralities, then one can see these differences. And thus, we thought so that it would be important so that theoretical models can also try to measure moments, how they are predicting, and then to compare with experimentally measured moments in order to tune their initial conditions, because all that comes because of the initial state fluctuations.
Okay, thank you. More questions? No. Let's thank the speaker again. Following an inquiry from the speaker, next talk is postponed for some later time. So we have a break until 11:55.